Hello. Uh, this is a video on treating light as a wave. As we said in the previous video, light can be considered either a wave or a particle. In actuality, using de Broglie's duality of light, um, you can use light as a particle, a discrete packet, and a wave, which is a continuous thing goes on forever at the same exact time, which is counterintuitive, but it's counterintuitive because we live in a classical mechanical world, and light and other things, other particles, live in a quantum mechanical world, which we'll discuss in another video. So, with light as a wave, I showed you in this picture, I showed you a couple of waves. Waves have certain characteristics that you supposedly already know. One is speed. We'll use just the speed of light. I give it to you in basically two unit sets. Frequency, which means basically if you are standing at a point and a wave is going by you, it's how many waves go by you in a given second, as long as you're not moving. Um, the units are something called hertz or 1/second. They're equivalent to each other. And the other one is wavelengths, which have a symbol of lambda, which is a backwards H. It's a Greek letter. And that is wavelengths, which is a distance in meters or nanometers. The way the equation that relates them is that speed is equal to frequency times wavelength, which this picture or these two waves show that the low frequency produces a greater wavelength, and a higher frequency produces a shorter wavelength, which would tell you, just like the equation does, that frequency and wavelengths are indirectly proportional to each other. As one goes up, the other one goes down. So we'll actually use these in calculations. Before we get to the calculations, I do want to show you what I call the family portrait of energy. Energy comes in a lot of different names. So would be like if you had all your aunts and uncles and cousins and everybody coming together, and you have one of those family pictures. This is the family picture for energy. It's called the electromagnetic spectrum, and they're all what they call forms of radiation, which is radiation is another way of saying energy. There is a link if you want to this picture, so you can just copy it. So what it is, this is electromagnetic spectrum. The wavelengths getting shorter as you go from left to right. The frequencies therefore would be getting higher if you go from left to right. And it gives you some normal materials, normal I don't know what the word is to indicate the size of the wavelengths for the various types of energy names. As you can see, there's radio waves, microwaves, infrared, visible waves, ultraviolet waves, and the one below it is just the visible light, the ones that we see, and it goes. It is Roy G. Biv. Okay, in this case, Roy G. Biv backwards. The violet is at the 400, and the red is at the 700. We're going to say. And the big thing you need to realize, and these units are in nanometers, that the colors are not don't create equal distances between 400 and 700. They're at different wavelengths in nanometers. for the colors. So you're going to be getting a color chart that tells you that. But you're going to have to memorize, out of all these things, what you memorize is Roy G. Biv, in that above Roy G. Biv, in this case to the right, the next name a region of energy is called infrared. You need to know that. And the one to the left of or lower wavelengths of violet is called ultraviolet. Okay, so what this is a picture of is, again, just the energy in all its different forms. And as you can see, the visible light is just a small fraction of it. But we're going to use it because of our atom. So now to do a calculation, I have an example. Again, you can go to the previous page to get a copy of just the question if you want to write it yourself. Okay, so the question is, what is a wavelength in nanometers of light that has a frequency of 5.34 times 10 to the 14 hertz? Now, if you're going to be using hertz, what I'm telling you at the first is don't use the 3.00 times 10 to the 8th meters per second, because a hertz is not isn't in that unit. What the better speed of light constant value should use is 3.00 times 10 to the 8th meters times hertz. Remember, a hertz is 1 over seconds, and that's why the hertz is times the meters. And that will help you out because now you can see that the hertz is a unit in there. So the question is asked for wavelengths in nanometers. You're given the frequency and you're given the speed of light in meters times hertz. Again, you're starting using dimensional analysis. If you're looking for one unit thing, you start off with 1 unit. What you have to do here is you have to look to see that the conversion factor, which is the speed of light, both units are in the numerator. So therefore, to cancel, you're going to have the first thing we start off with on the bottom. So you're going to take 1 over the frequency, multiply it by the conversion factor, which, as you can see, there's no 1 over the other because it's all being multiplied, so that stays on the top. And since the question's asked for nanometers, we're going to get meters, so you have to go from meters to nanometers, which you know, and you end up with 561.7 nanometers, which is equal to 562. Interesting. That's wrong. It should be 562 nanometers. Okay, and why 3 significant figures? Because besides the fact that that's how many, the last step is multiplication, and then therefore you look into the numbers in the question, and there are 3. I am going to tell you that every single calculation you do for these types of problems, you're going to have 3 significant figures. I'm going to make it that way. Okay, so that's by dimensional analysis. By equation, you do the same exact thing, except what you know, what you're looking for. And the equation is the wavelength times frequency is equal to the speed of light constant. So you then manipulate the equation to get wavelength is equal to speed of light over frequency. Okay, so then you plug in, and then you get 5.617 times 10 to the minus 7th meters, which you then have to change into nanometers, and then you get 561.7 nanometers, which again ends up being 562 nanometers, not 561 like the like the handout shows you. Okay, I had a rounding problem there. So that's how you do calculations for light equations. So this was a video on how to do light equations, and also explaining about how the fact that light is a wave, we have the frequency in the wavelength, and that wavelengths, we call certain wavelengths in a very small range, are called colors. So thank you.